Welcome back. In the last module, we talked about anomaly detection via density estimation, which came as a very natural approach once we convinced ourselves that fitting a direct mixture model, as it was specified in the contamination framework, is usually practically not feasible due to the low number of anomalies or the low fraction of anomalies in the dataset and the difficulties of identifying anomalies by hand. In the next modules, we are going to talk about different philosophies of how one can identify anomalies. Although the ideas often seem very different from density estimation, they all work around the idea that anomalies do not appear in areas where the data is very densely clustered, and so they all have relatively tight connections to density estimation, which we will investigate in the following. So now we are going to talk about anomaly detection via isolation. So the idea is now that an anomaly should allow simple descriptions that allows us to distinguish it from the rest of the data. So for instance, if you look at the image below here, these orange dots are our anomalies. And let's say the language in which we want to distinguish individual points is the language of straight lines. So we want to try to find straight lines that separate individual points from the rest of the data. Then we can see that when we write in the cluster of this gray data, then we can see that there is no straight line that allows us to distinguish any of these points from the other ones. While for the orange ones, it's rather simple. So if we take the upper one here, then for instance, I easily separate it from all the other ones. Even more, it's not only the case that we can find one such distinguishing description. In general, it will be the case if a point is really anomalous that we can find many such descriptions. Again, here you can see it doesn't matter whether the line goes like this or maybe a bit more like that. We can find a lot of these separating lines that distinguish these points. And this is what we're going to use in the following. Moreover, we want to have a technique that is not only able of identifying anomalies, but we also want it to be highly performant, meaning that the computations are all easy to perform, easily parallelizable, and scale better into higher dimensions, which was one of the major drawbacks of KDE, if you remember, the last module. So taking all this together, we arrive at the following idea that we want to use separating half spaces, but in order to make the computations efficient, we want to have them axis aligned. So meaning that we're testing whether a certain feature of a point is smaller than a given value or larger than a given value. Our description will be conjunctions of these tests, where we measure the complexity in the number of conjunctions. Finally, we incorporate the idea that there should be many separating descriptions by assuming that a short random description will have significantly higher chance of separating an anomaly than any other point in the dataset. So what we are going to do is we are going to create many separating descriptions and then compute the average description lines for them. Again, we want to do that in the most efficient manner. And in this way, we would like to do in one pass compute separating descriptions for all points, and then repeat this several times in order to compute the averages. Okay, as I mentioned in the last lesson, we first want to compute separating descriptions for all the data points in the dataset. We are going to do this in a tree-like fashion so that we can reuse as many tests as possible for as many data points as possible. So how does that look? So we start with the dataset or a subsample of the dataset and a maximal height. And then we randomly choose a feature I and a split value S, which we computed from the range of the data. Once we have our test, we can separate the dataset into two parts, the one where the feature I is lower than our value S, and the ones where the feature I is larger than our value S. Now we can recurse on the two subsets that we computed and successively build a tree in this manner. We stop if the maximal height is reached or if we have managed to single out a single point in one of the leaves. So finally, we need to store all the tests that we use in the inner nodes of the tree and the number of remaining data points in the leaf of the node. In the following, we are going to talk about how to compute a score from that. Alright, now that we have an isolation tree, we can see how to compute an anomaly score from that. So given an observation x, we can now start at the root and follow the tests that we've computed in the inner nodes. So this will give a unique path from the root to one of these leaves. Let's say this length is L. So it might happen that at this place there were still more than one node in the data set at this leaf. So we'll call this number n. We want to compute how long we would have need to proceed with our splitting procedure in order to separate all of them. And for that we take a well-known number, C of n, which is the expected length of a path in a binary search tree where n nodes are inserted. This is about O of log n. So finally, here our isolation depth, h of x, will be L, the length from the root to the leaf, plus this estimate of how long we would need to proceed splitting in order to separate all the points, which was C of n. So reason why we stopped at some point is that these trees become very large as we increase the depth. So usually you would choose for the maximum depth something like 5 in order to let these trees not to grow extensively. So now we do not only want to compute the isolation score for an individual tree, but we want to do this for an entire forest and then average the anomaly scores that we got. Down below you can see one example of how this might look like. Here we have one point which was in the center of the distribution that you've seen before. So let's go back for a moment. Here you see the blue dots are the nominal points. And maybe you can even spot, like right in the middle, there's a green point. This is where this blue line belongs to. And here we have this red point, which is the anomaly. And here you see the isolation depths for different isolation trees. The blue ones, again, are the nominal points. You see we always reach the maximal depths for this point, while the red one was the outlying anomaly. And here you can see that the isolation depths are on average way lower than for the nominal point. So this is the entire algorithm of isolation trees. As you see, it's quite similar to the well-known random forest that you might know from classification tasks. And similar to the random forest, this isolation forest has the reputation of working rather well, even in relatively high dimensions, and even without extensive hyperparameter tuning. So let's talk about a few variants of the isolation forest. The first comes from Amazon and is available on their AWS platform, and they call it the random robust cut forest. The only real difference between the random robust cut forest and the isolation forest is the splitting rule. So remember that for the isolation forest, we have chosen the split dimension uniformly at random. The same it holds for the split criterion. So now we're going to change that. We're going to look at the length that is still present in the data with respect to the ice component. And we are going to do that with a probability that is proportional to this remaining length. So first of all, they claim that this is more robust against noise dimensions. So for instance, you can imagine that you have a data set where there are only one or two really important features, and in all the other features there's just some small noise present. Then the original implementation would just prefer the noise dimensions equally well as the dimensions of relevance. So while this implementation would recognize that there's only little variation in most of the dimensions and would prefer the relevant ones. This is something that can be seen in the example that you see on the right. So the left image is from the original implementation, while the right image comes from the random robust cut forest. And you can see that the tiles that are generated by the random robust cut forest are much more balanced than the ones that the original implementation generated. So you see these long, thin areas that were created by the original ones, such are way less present in the random robust cut forest. So it has another important advantage, and this is basically why it was generated, is it very well suited for time series analysis. In time series analysis, where you usually expect your distribution to have some shift over time, you don't want to train on the entire history, but potentially only on a window of the last history, a sliding window that moves over time. In this case, for the original implementation, you would have the problem that you would need to recompute the isolation forest every time you move the window. And this is something the people from Amazon have proved is not necessary for their variant. Here we can just remove the points that fall out of the window and reinsert new points as they come in, and it's probably the same distribution as if we would have recreated the tree. So this is the major advantage of this version. Another variant that I would like to mention is the extended isolation forest. Here we again choose a new splitting criterion, but this time we allow not only to choose axis-aligned hyperplanes in order to separate data, but we allow arbitrary hyperplanes. In this case, we do not only allow the separating hyperplanes to be axis-aligned, but we allow arbitrary hyperplanes to separate the data. So this effect gets mitigated once we allow arbitrary hyperplanes. On the right, you see the result that we got from the extended isolation forest. In this case, the result looks much closer to what we would expect to get from a KDE, for example. There is certain evidence that the extended isolation forest does not scale as well to higher dimensions as the original implementation does. One reason for that is that they are connected to different measures that I can put on the space. While the original implementation is highly connected to the L1 distance, the extended version is connected to the L2 distance, and it's known that the L1 distance had slightly better properties in higher dimensions. So this concludes our part on the isolation forest. Next, we are going to apply this technique to a standard benchmarking dataset. In this exercise, we are going to apply the isolation forest to the KDD-CUP99 dataset. This is a synthetic dataset created by the DARPA in 1998. It simulates attacks against a computer network. In case you're interested in details of the dataset, we refer to the dataset's homepage, where you can find detailed descriptions of the individual features and everything else that can be important to solve the task. So please work through the cells and we see each other again with the solution. All right, I hope you all got a chance to go through the notebook. Let's review what we've done there. So first of all, we got the data and then started to explore the data. First of all, since not all columns are continuous in value, like the standard describe function won't give you like very good results, it's better to first remove all the non-continuous feature, then we can get a better description directly. We did that here. So we see, first of all, nothing too special here, nothing that comes to our mind where we should definitely take action. So we continue. We check if there are nonce in the data that could disturb our procedure, which is not the case. We do a little bit of data pre-processing. In particular, the categorical variables need to get binarized. This is done in this set here. And finally, we do a little bit of pre-processing. We try to apply a simple heuristic to remove potential anomalies. Remember, although in principle we have labels for this data set, in general we want to work as if we don't have them, because this will be the much more common situation that you find in practice. So here we really apply just a very simple heuristic in order to get rid of values that are suspiciously large. So here basically for each column we took 4 times the standard deviation and checked if values are there that exceed this number. So you might be tempted to estimate some probability out of these 4 sigma, but please be careful if you do that, and keep in mind that we're looking at 41 features simultaneously. So of course, I'm looking at 41 features. The probability that one of these features will exceed the 4 sigma is definitely larger than what we would expect when we just look at one feature. So please just take this here as a purely heuristic rule. it's not so easy to directly compute probabilities out of that. Anyway, we can still see that there's less than 1% of the data which fits to our suspicious criterion. So I think in this case that might be actually a good idea to take them out. So now we create the isolation forest. And as I've mentioned previously, the isolation forest claims to work rather well out of the box without much of hyperparameter tuning. So this is something that we're definitely going to test here. We create our test and train set, our validation set, fit the classifier, compute the stores, and take a look at the ROC curve and the AOC curve. And you see again, outstandingly good results in this case. Like numerically, the ROC AOC is already at 1.0. Also, the PR is with 9.5 extremely high. This is partially due to the fact that the KDD-CUP99 dataset is known to be not very hard. So the attacks really produce very different observations from what you would expect from normal connections. And this is something that we could replay very well in this exercise. In the next module, we are going to talk about deep learning methods for anomaly detection, more precisely about anomaly detection via reconstruction.